All right, so hi everybody. So today we have the pleasure to have Shu Ding, assistant professor at University of Florida, who's gonna talk about volatile in volcanoes and especially the codes that we can use to estimate degassing from volcanoes.
Thanks, Sylvan, for the introduction, and thanks for having me, and thanks for having the SulfurX on, Victor. I'm now at the University of Florida, and I actually just started in January, and my research is on volatile behavior in volcanic processes. But before joining UF, I was such a research scientist in Lamont. So many of the work I presented today was done at Lamont as well. So here. So this is a very brief outline of today's lecture. So I will briefly introduce volatile degassing in general, and then the mechanism of sulfur degassing, our understanding of how sulfur behaves particularly, and then what is SulfurX, and then there are some. Then in the end, I will show go through SulfurX on Victor, and what are the potential applications. Okay, so for volatiles, so basically, magmatic volatiles here we're actually mainly talking. We are talking about water, CO2, sulfur, chlorine. But for most of the volatile degassing models, we are dealing with water, CO2, or water, CO2, sulfur. So there's a lot of work done in terms of halogens. So water is the major one. We're talking about weight percent in magma, and sulfur and CO2 are minor. Then we're talking about ppm level, but sometimes recent studies basically show some magma can have actually up to one weight or more than 1 weight percent CO2. So it could be also major depending on the magma composition and conditions. So when we talk about volatiles, most we're interested in, of course, what is the total gas fluxes, right? How much SO2, CO2 can be released through volcanoes, and CO2 sulfur ratio, the SO2 fluxes and CO2 sulfur ratio is also some of the major parameters that has been regularly, frequently monitored at volcano and many active volcanoes now. And then how much we also care about how much volatiles can be dissolved in the magma. For example, how much water can significantly affect the melt viscosity, and then when and how much volatile can exhaust from the magma during magma ascent, because they form these vapor gas bubbles would significantly affect the magma compressibility and buoyancy. So basically, these are important parameters when going into other models, when we want to model conduit process. So that's why it's really important to understand the behavior and also have some kind of models can calculate how much volatiles are dissolved in the magma given certain pressure, temperature, and magma composition, and how much can be exhausted. So during this, so we are mostly, so for modeling volatile behavior, we are mostly looking at this vapor magma equilibrium. And then different volatiles, so if we're looking at water, CO2, and sulfur, these three, they actually behave very differently. And then so for solubility, meaning the maximum amount of these volatiles can be dissolved in the magma. It's for water and CO2, they're very sensitive to pressure change. So as pressure decrease, the solubility can decrease significantly, and that would trigger bubble formation, volatiles go into these vapor bubbles. So for CO2, they're actually most sensitive, and they start degassing really early. So this sketch is basically if we have CO2 concentration on the X, and then this is pressure. So as pressure decrease, we are mostly looking at a CO2 solubility curve like this. So we can see CO2 starts to decrease in the magma and go into this vapor bubble at very high pressure. So another way we look at volatiles or study volatiles is we actually look at melt inclusions. So these little melt bubbles entrapped inside the crystal. So the nice thing of melt inclusion is that ideally they stop changing after they were entrapped. So basically, it gives us a snapshot at the moment of the magma when it was entrapped, like how much water and CO2 are dissolved inside these melt inclusions, can actually give us a sense of what is the entrapment or saturation pressure. And that is mostly rely on this pressure sensitivity of water and CO2 solubility in the magma. So if we measure what is the water and CO2 in this little melt vapor, well, they have to be glassy and no crystals. And then we could actually we could calculate what is the pressure of this entrapment pressure of this melt inclusion. So if we have a lot of melt inclusions that were entrapped at different pressure, then we could actually ideally we could plot the water CO2 and versus the saturation pressure that's calculated. So we could see how water, CO2, and sulfur, if we measure sulfur too, change as a pressure change during magma ascent. So that's like one ideal way of tracking how volatile behave in the magma during ascent. Of course, we need to assume that there's no post-entrapment modification to the melt inclusion. For example, this vapor bubble is actually one of them played a major role, like the CO2 like changing CO2 budget in the melt inclusion. And also another assumption is we need to have a really well-constrained solubility model versus pressure. So we can get a good idea of what is the pressure based on CO2 water concentration. And it's not only that, we could also kind of infer, right? If we happen to have a melt inclusion that actually experienced very little degassing, then we could get a sense of what is the volatile contents in the parental magma as well. So melt inclusion is actually a pretty powerful tool to study volatile degassing as well. So most of my research is actually combining there's a popular approach is combining the melt inclusion and this degassing modeling, and now even like the volcanic gas data, which were collected at surface to really understand this whole process. So for the model, the volatile solubility, we just talk about pressure played a major role, and then temperature, melt composition as well. And for sulfur, the specific cases is very sensitive to FO2, the oxygen fugacity in the magma as well. So these kind of solubility model can be thermodynamically or empirical modeled. So in either case, the calibration of these solubility models are usually used like high pressure temperature or high temperature at 1 atmosphere, solubility experiments. Because experiments, basically, we do it at a fixed pressure and temperature, so we can we control the starting composition of the magma. So all we need to do is to put volatiles in it and then to see what's the solubility and measure them. So that's a pretty nice way of, or essential to construct this volatile solubility model is to have, enough experiments. Okay, so there are a lot of CO2 water solubility models are more in advance compared to understanding sulfur, and sulfur now is, as I said, is more in advance compared to halogens. So here there's a very nice paper on Vesical. So kind of have a really nice summary of different existing water CO2 solubility models. So if you are interested in a system that is only CO2 water bearing, this is a really nice, all these models are available. So let's go into the sulfur. So sulfur is like different. So conventionally, sulfur is really assumed to be degassed only at very low pressure. So if CO2 solubility curve look like this, for a long time, sulfur solubility or sulfur degassing curve really look like this. So it only starts to turn at this like really shallow pressure. We're talking about maybe like less than 50 megapascal or even shallower, or 10 megapascal. However, sulfur is actually also more complicated because it's a multivalent element. In the magma, we're really not look at sulfur as zero, but we are really thinking about sulfate as 6 plus and sulfide as 2 minus. And then in the vapor phase, sulfur is also multivalent. So the major species, we're talking about major because there could be others very minor as zero. So H2S and SO2, and these two are also very often measured in volcanic gases. So we are looking at, so basically when we talk about sulfur equilibrium, we're looking at multiple equilibriums between these different species, right, in magma and in gas. So what controlled this sulfide or sulfate speciation in the magma? There are experimental studies. Basically, we're really, so that's strongly controlled by the ferric-ferrous ion ratio in the magma, which is a function. It's usually a measurement or index of magmatic FO2. So this is basically the equilibrium we're looking at. And then we can also, and then in the vapor phase, we can also write out the equilibrium. Again, it's relevant to FO2 in the system. And for this reaction, we could actually calculate what's the H2S SO2 ratio in the vapor, which is a function of FO2 and the temperature. So both are like strongly affected by temperature. So that's why temperature is actually an important input of modeling this. So here we can see a more, this is basically sulfur speciation change in the magma as change. So x-axis is the FO2 relative to FMQ buffer. So like most magmatic system, right, from morb to arc magma, we're really looking at maybe slightly below FMQ to FMQ plus 2, or even some are even more oxidized. So these are really where we are interested in on Earth, magmatic system on Earth. But we can also see, so this reddish shades is basically how sulfate over as total sulfur speciation change in the magma. We can see where we're really interested is also where all the changes could happen, and very sensitive, because as you go more reduced, it will be always sulfide only, and as you go more oxidized, it will be always sulfate only. Then that's less complicated, but where the most interesting, like most of the dramatic change happens is actually the most interesting place, like in the magmatic system on Earth. And then we can see the similar things to the gas equilibrium as well. So these green shades indicate the SO2 over total sulfur in the vapor. That ratio also change, also quite sensitive to this region of FO2. So in order to model sulfur degassing, we really need to figure out we really need to handle this multiple the speciation change in this region, and we need to take into account the FO2 change of the magma. So this figure, we can see FO2 does affect sulfur degassing, like how much sulfur go into the vapor as well. So here in Y, we're plotting this thing called sulfur partition coefficient. That's like one way to actually indicate how much the preference of vapor to melt of sulfur. So basically, partition coefficient is a ratio between the sulfur concentration in the vapor and divided by the sulfur concentration in the melt. So this can be written either in weight percent. So then both are in expressed in weight percent or molar percent. So when you use sulfur partition coefficient, one thing needs to pay attention is, okay, well, are we talking about the molar partition coefficient or weight partition coefficient? So we can see that, so all these symbols are experimental data. We can really see that there is a general increase of sulfur partition coefficient as FO2 increase from -1 to FMQ +1. However, then after that, there is a general decrease. So that's why it also made it more complicated to model sulfur degassing, because this complication, this maximum sulfur partition coefficient happened in this intermediate FO2. So basically, so for the newer models that are dealing with sulfur degassing, because of this different speciation thing, so most of the model would treat actually sulfur, like different sulfur speciations separately, and then one can actually write reaction for each for its sulfate and sulfide. So in SulfurX, we're kind of adopting these two reactions. They're all pretty similar. Here we're talking about sulfide in the melt, and then plus water in the melt to make H2S in the vapor. So that's how we look at sulfide degassing. So sulfide, water to H2S. And then for sulfate degassing, we're only looking at sulfate degas to SO2 in the vapor. But here, so we can see the first reaction is really relevant to water, but it should, just looking at this reaction, it should be inert to FO2 because there is no valence state change here. It's S2 minus in the melt to S2 minus in the vapor. But then the second one, since there is a valence state change from S6 plus to S4 plus, so this reaction, just looking at this reaction, should be sensitive to FO2. So based on these two reactions, so the next we're going to look at is a few different ways of approaching how modeling sulfur degassing. So first of all, in the early days, it's really people are just model this partition coefficient. So there is a very commonly used model called SulfurX. So this SulfurX is basically just used a bunch of experiments from this Lansney et al. 2011. So they run experiments at different pressure and then kind of calculate what's the sulfur partition coefficient among pressure. And then SulfurX basically kind of parameterized this change as pressure. So it comes with this equation to calculate what's the sulfur partition coefficient here. So one need to pay attention here is these experiments are only done for this range of FO2. So if you really want to apply this, just do a quick calculation of your sulfur partition coefficient. This has to be within this FO2. But then there are some potential problem of the experiments that's used to calibrate this model. So if one use this model, so some cautions need to be paid. That's then as it continues develops, there's another very commonly used model called decompressed, and this model actually deal with not only sulfur but all different kind of volatiles, and it's more thermodynamically vigorous compared to SulfurX. So in terms of modeling the different different melt gas equilibrium, they really consider this kind of solubility law, basically right in this exponential format. So for sulfur particularly, so this is they consider SO2 and H2S separately. Again, because of the sulfur speciation issue, and then for each speciation, they're using experiments to basically calibrate empirically to regress for this term A and term B. So you can calculate what is the sulfur SO2 and H2S in the melt dependent on the fugacity in the SO2 H2S in the vapor. So this is decompress. So basically these commonly used sulfur degassing models by before 2019 or by 2019 when I was started working on SulfurX is kind of it says they are summarized in the table in my in the SulfurX paper, so we can see like how they are constructed, what's the approach, and then when how did they deal with FO2 and what is the pressure range. But then after that, like when I started working on SulfurX, there are actually many other newer models was like started, like people are all working on how to model sulfur degassing. So these newer models, many of them are actually taking another approach called kind of like sulfide capacity and sulfate capacity. So basically so this controls how much sulfide and sulfate, again, still sulfur is dealt by, using two speciations. Basically it's like kind of two volatiles instead of one. But instead of using the partition coefficient, it's basically the sulfide and the sulfate capacity. But again, these are also experimentally calibrated. And for sulfide and sulfate capacity, I think I don't know if there are new experiments, but the ones that are existing at that time is all at 1 atmosphere experiments. And then people kind of like treated the pressure effects separately, kind of try to extrapolate to high pressure. And then, so now here comes SulfurX. So we did not really take the sulfate capacity way, but we were actually still using the sulfur partition coefficient here. And the SulfurX actually also deal with, by the way, this new model, they also like dealt with multiple volatile species. So not only sulfur, but also water, CO2, sulfur, and all together. So for SulfurX, yes, we are trying to model sulfur CO2 water evolution in basaltic magma, okay, and then coexisting vapor. So what the approach we took is actually kind of combine the sulfur partition coefficient with the existing CO2 CO2 water degassing model. So we use the existing COH model. And then we also kind of managed to model the sulfur speciation, like how FO2 change along degassing in the magma system by using this redox budget conservation between sulfur and iron. But we only consider redox reactions between these three species in SulfurX model. And so here are my three co-authors. So this project actually is mostly done online. So we started working at like 2019, 2020. So here, as we said, for SulfurX, we use these two reactions to govern the two sulfur species degassing. So sulfide degas to H2S and sulfate degas to SO2. And just by looking at the reaction, we kind of know what for each species the governing factors to these degassings are actually different, right? So for the reaction one, we call it reaction one, the sulfide degassing, we can see water and iron concentration played a role. And then for the second reaction, we can definitely see FO2 and some K-time like calcium or other K-time that could be combined with sulfate could play a role too. So based on this, we kind of, so this is really one of the core development of SulfurX is we actually redeveloped these two partition coefficient corresponding to sulfide and sulfate degassing. We not only carefully choose the experiments that are only done in the FO2 conditions are relevant, only relevant to sulfide or sulfate, and we also considered the pressure and temperature effect in a more thermodynamic way. So these basically governing this is basically how we treated the two different partition coefficients. So we can see pressure, temperature, and then for sulfide degassing, water, iron played a role, and then for sulfate degassing, pressure, temperature, FO2, and then the melt composition all played a role. So then after that, so for SulfurX, we actually then we combined these two partition coefficient using the sulfur speciation in the melt to have one partition coefficient. Then we calculate the sulfur degassing. So this is basically one of the results figure in the SulfurX paper, kind of showing us is, so we can see as predicted for reaction 1, it doesn't, so X again is the FO2 change. So reaction 1 doesn't really change as FO2 change. And then reaction 2, which is sulfate degassing. By the way, the size of this little circle is indicate how much of each speciation present in the melt, right? So at very reduced one, there's very little finite amount of sulfate in it, and then but then we can see the KD of reaction 2 sulfate degassing actually decrease as the FO2 increase. So then we combine it. This black line is the combined partition coefficient. Then we can see this combined partition coefficient can actually nicely track what is shown by the experiments data, what we saw in the earlier figure, to show this maximum sulfur partition coefficient around FMQ plus 1. And then using different sulfur speciation, we kind of see, okay, sulfur degassing can actually behave very differently depending on the sulfur speciation. So for the yellow curves are very oxidized, has 70% sulfate, and the greenish group is actually kind of reduced, only have 10% sulfate. So we can see these two groups, they behave pretty different. And then another difference is showing in this diagram is the concentration of water. So the lighter color ones are the high water one, and the darker color ones are the low water one. So we can see as water increase in the magma, regardless of sulfur speciation, sulfur tend to be degas earlier at higher temperature in the magma. And if it's a very dry and reduced magma, like this dark green curve, then that's what we look at, like sulfur only degas until very shallow pressure. Okay. So for SulfurX, we kind of, so one of the core developments is we come up with like a new set of sulfur partition coefficients, but we did use existing model to kind of, model the whole system. So there are existing COH degassing models. So there are a lot, but in SulfurX, we provide you like two choice. One is this a volatile calc is a kind of a old model. It's still pretty good at modeling warp or dry shallow degassing. And then we have a newer version, newer COH model, Incano-Marciano model to choose from. You can model like more oxidized and wet, like wetter magma, and also the experiments are done like at higher pressure. And then another key factor here is we need to know what's the sulfur speciation, how to relate it to ion speciation, which is the FO2. So there are several models available, so we kind of put all the available models there. But just to keep in mind, none of these models is actually perfect. So when choosing these set of parameters, you need to kind of, depending on your model, the system you want to model, what the temperature, and if it's dry or wet, you might want to choose this. And we also kind of provide a option, is because this Muth model is really an empirical model. So we kind of provide an option that you can actually revise the Muth model to based on this to fit your own data. So if you actually have your magmas, your system, you know what's the ions and sulfur speciation change you measured by Zense, then you could actually use this option to kind of fit your data to see which one fits your data the best, and then choose. And then the last is this how ion speciation connected to FO2. Now here we use the Kress-Carmichael model, which is classic, and also many other system people are using, like whenever they use calculate FO2, this is one of the most commonly used one, but there are new models existing. Okay, so here in this slides basically is showing what kind of system can can be used for can SulfurX to model. So one thing is basically so these are all the experiments that are used to calibrate SulfurX. So here we can see is really for composition, it's mostly basalt. There are a little bit andesite here. So I would say I would not apply this to dacite or rhyolite. So basalt or basaltic andesites, that's like the composition. And then the temperature range, we can see it's between 1,000 to 1,300. That's mostly decided by the liquidus temperature of this melt composition, right? And then pressure range, again, we are trying to include all the like as many runs as possible, but then we also want to choose, right, for sulfide degassing, we want to choose only reduced one. For sulfate degassing, we want to choose oxidized one. So here we have 1 atmosphere to 500 megapascal, which is pretty good. But the thing is, we still want to be cautious about it because the pressure range has been always played a limit for many other models as well. So that's one thing to keep in mind when we use all this degassing model. If your model system like really deep, like 600 or 700 megapascal, just keep in mind it's actually outside of, I think, pretty much any current existing degassing model in terms of pressure. And so this is just showing the pressure and temperature range. Okay, so let's go to the application now. So I'm gonna open the here. We're on the Victor. So for application, we're mostly looking at, one thing, because we started doing this to kind of model melt inclusion data. So there are a few more applications on melt inclusion data, but then I'm gonna also kind of talk about another application I recently kind of did, is basically to interpret what's the CO2 sulfur ratio that in the volcanic gases. All right, so let's go to the Victor. I wonder if I can, yeah. So I have already opened this. Is that okay? I guess everyone knows how to like open through the Victor setup and then just pick which model you want, right? So it's Victor setup. And then SulfurX, and then I just do SulfurX. I think for me, it says already exists. So that's what I have installed. Okay, so here we are basically looking at some basic parameters. So there are some basic input here. So this temperature, as we just mentioned, temperature is actually pretty important to it will affect the calculation of KD. But it will also affect calculation of ferric, ferrous ion, sulfur, sulfate speciation, and SO2 speciation. So it will be good to know the temperature like relatively well. And then FO2, again, it's the input is actually relative to delta FMQ. And then you will use it to calculate the initial ferric ferrous ion ratio and sulfur speciation. And then we need to know initial water and CO2 in the magma. So that can be, if you do like melt inclusion study, that's basically you can use your highest water and CO2 concentration that's measured in your melt inclusion, and then initial sulfur. So the way SulfurX initiate how degassing starts is actually use the initial water and CO2 to calculate what is the saturation pressure. So we assume at that highest volatile you measured in your system, the vapor starts to saturate. That's where the degassing path starts. That's your initial pressure. And then you have the sulfur initiation. What's the how much sulfur the system starts with. And then crystallization is basically a yes or no question. If you want crystallization, you do 1 or no 0. So SulfurX, so I'm going to talk about a little bit about crystallization later, because it's not like it doesn't really model crystallization process itself. And then there is the total step of pressure from the steps. So SulfurX does this like by decrease a little bit pressure and then decrease more. So you can decide how many total steps you want to run. 300 is usually a pretty good number, but for some, but this is also one of the parameters you can change if the model has a pretty big oscillation. Maybe it's because the condition changed too much, because SulfurX you always use the previous step as an initial guess to solve the next step. So maybe if for some calculation you could make it larger to to come up with a smoother solution. But sometimes if it's too many steps, it can also cause a lot of swing, especially if you want to track FO2. And then this is the M is actually basically total number of runs that you want to run. So total number of not the runs actually, it's total number of steps you want to run. So basically if these two are equal, meaning you want to run all the way to surface. But you can just say, okay, I only want to run like 2/3 of the pressure range. I don't need it to be all the way to surface. Then you can say, I want this number to be 200, 250. Then that doesn't run to the surface. And so these are the so okay, so then the specified models to use. So that's where we talk about there are multiple models, right? We can use it to track because SulfurX is actually combining these different models. So for COH model, again, we provide these two options, volatile calc or Incano Marciano. So you need to choose that. And then for sulfur ion speciation model, again, we talk about it. There are 3 models to choose, and you can also modify it. And then the FO2 is basically another yes or no question. So if you want to track FO2, you say yes. So for FO2 is what my recommendation is. Even you want to track FO2, if you are dealing with a new data set, the best is you don't track FO2 first. So you turn this off because the calculation is more complicated. What I usually do is I turn this off and then just choose these 2 parameters and to see and make sure all these are correctly chosen, appropriately chosen. That model can actually run all the way to 1 atmosphere. And then I add this 1 layer of complication to track FO2. And then we have, so here, there is an option you can actually read in your own melting inclusion data, and then later the plots would plot it. But this melting inclusion data is not used in calculation. It's only used for plot. If you don't have that, it's okay. Just you can leave it there. So it's going to be always plotted the Fuego melting inclusion that I used to first develop SulfurX. Well, not used for calibration, but mostly. Okay, and then this is your output. So in the end, once we run that, there is going to be a set of output files to have all the results. So this, you can give it a name, you can change the name, and it's going to be output as CSV file. Okay, so then this is the save, that's fine. And then, so how SulfurX deal with the errors is really through, change Monte Carlo simulation. So basically, the error we count here is only through the errors that come from the sulfur partition coefficient. So what it does is at every step, if you choose this choice, at every step, instead of using the calculated sulfur partition coefficient, it's going to choose a random number within the error of the sulfur partition coefficient. And then in the end, you will then that will, so, and then you can decide if this is a yes or no, 1 is yes, and then you can decide how many Monte Carlo simulation you want to run, so that you will have multiple degassing paths. So in this way, the output file, it will give you a file. Basically, these 2 files will be output file. It will only output, 1 is the sulfur concentration in the melt. So in each path, each Monte Carlo simulation, it will be different. And then another one is the sulfur CO2 sulfur ratio in the gas, because these are 2 kind of I'm most interested. So you can decide how many rounds you want to run. So this melt fraction should be always 1, I think. And then the ink, the INC, so these 2 is only relevant if for some reason, because the sulfur partition coefficient gets really, really large at low pressure, like close to one surface. And if you really always have really large oscillation there, what you can do is actually you can say, okay, I want to increase the KD like manually, like arbitrarily myself. If you also, especially if you have a sense, what is your partition coefficient at surface should be close to 1,000. So you can actually manually increase that KD. So this is where you input that number. And this bar is basically say, okay, below this pressure, my KD become, so I can manually increase the KD. So this bar is pressure in megapascal. So I can say, okay, below 1 megapascal, I just want to manually change the KD to ensure that my run goes to the surface without a really big swing. But usually, so that's one. And this one, if you turn off the FO2 and then you can still not have a really smooth run, this might be something you could play with. But if you use this function, in your application or in your paper, you might want to mention this, right? Below 5 megapascal, I'm actually increase KD by this number instead of using the calculated KD from SulfurX. So this set is basically to if you know your system have a sulfide, you can use these to input your sulfide composition. But for now, SulfurX actually doesn't deal with the situation that sulfide is saturated. So this is really used to only calculate the sulfide solubility. So what you can use is in the output file, there's going to be sulfide solubility. So you can actually compare to your sulfur calculated in your Magma to get a sense if actually it's sulfide saturated. If sulfide is saturated, then you might need to think about, okay, maybe this degassing pass, it's not too valid because it's actually sulfide saturated. So these three sets is so this sigma is actually a tolerance. So when we calculate the FO2, we're kind of like taking a alternate, like a iteration way until the FO2, we calculate FO2 in two different things until they agree. So this is basically what is the small difference between that two sets of FO2, and then we agree this is what we reach the internal consistent FO2 through the system. So this actually is very, very important if you want to make your FO2 run smoothly. You really want to kind of play with this number. Sometimes if it's too small, you actually get, right? Ideally, you think, oh, if it's too small, it's good. But sometimes you want to make it smaller and sometimes you want to make it bigger. Of course, you also don't want to make it too big because then that basically is different FO2. Then that's not. The unit is actually log 10, so keep that in mind. So I usually between like 0.1 to smaller than 0.05 would be ideal. And then the last I want to talk a little bit about is how SulfurX deal with crystallization. So it can use, so if you know your system does have a pretty obvious crystallization trend, you can actually change your melt composition, like how it changed in crystallization in this melt composition file. So you will have to go into this file to change it manually, unfortunately, because SulfurX does not models crystallization itself. So here you can input how your different oxides is changed as a function of melt fraction. Okay, so that's what this melt fraction is for. So here is use actually potassium as a index because potassium is always perfectly incompatible. So you can calculate, right, how if you have a set of melt composition change, what you could do is maybe use either like melts or other things to model and then parameterize how this can change and then input it here. If you know at some point, the melt composition changes just does not, very consistent or it stops changing, this is where you put that threshold here. So if you want to change, if you don't want to change your melt composition, so here's where you actually put yeah, so here is actually where you put your melt composition. So in this way, your melt composition does not change as fractional crystallization, but it only changes because of your melt fraction is changing. So it's kind of act as like a diluting factor, right? So this is where you can actually change your melt composition. But then the last thing is actually these two sets is when we actually count for crystallization, it actually related to water concentration here. So this is basically come from how water degassing is related to fractional crystallization. So you need to input a relation between, again, potassium and water concentration. So here is one set of again, this you can come up with it using your, either melt composition, or if you can just plot your melt inclusion data sets to see if potassium and water has some kind of linear relations. And that's where you put this, what is your slope of the water and what is the constant. So basically it comes from these sets of equation. And this whole concept comes from this Lloyd et al. 2013 paper. So if you want to know more about this, that's where it goes. Yeah, so basically we can, if we just run this quickly. So if we set all the parameters and run it, so I just chose, remember, we just chose the Monte Carlo simulation. Now it's gonna have like 3 runs. So it's gonna take, so these are basically how sulfur concentration, so these plots just come with the code, but you can always plot differently. So here is one of the main plots, so how sulfur concentration change with pressure, how partition coefficient change. And so we can see, because we use the Monte Carlo simulation, we can see we did 3 times. So this is how the results work. And then this is how the vapor CO2 sulfur ratio in the vapor change. Then that's what, so I usually would put it like, 300 rounds or 500 rounds, something like that, or even more, but then that's gonna take significantly longer. Yeah, so let's just take a look at the results. So these are the results. You can download, I think you can download this file. So these are all the important thing, FO2, and then this for melt, all these are expressed at weight percent, but then it also has the mole fraction, which is expressed at X. And then these are the phi is the fugacity coefficient. So it also outputs a lot of like important, and this is important thermodynamic parameters here. And these are the fluid or the vapor composition in mole fraction. So if you, and this is the melt fraction, vapor fraction, and crystal fraction if we enable crystallization. And these are different KDs. And another important thing people usually care is what's the SO2 over total sulfur in the vapor change, and then what's the sulfur speciation change in the melt. So all these are input. And then in the end, it also calculates if sulfide solubility. I think it's somewhere. Let's see where it is. This is the SCSS sulfate solubility and sulfide solubility. Then that's for comparison ratio, a comparison. So you can download this and then make your own plot. How much time do I still have, Sylvan?
Well, that's fine.
I'm over.
You can go ahead and finish. Yeah, no problem.
Okay. Go for it. Okay, thanks. So yeah, so there are some troubleshooting as we just talked about, and that's actually written in the supplements or supplementary in the SulfurX GCube paper. So basically, it's just what I just mentioned. You want to try without FO2 tracking first, and if you have a big swing, what do you do? But you can always shoot me an email, and if you tried all this, it didn't work, maybe we can take a look together. So basically, these are like some of the existing applications. For example, model, these are all melt inclusion data. We can model like wet oxidized degassing, and we also use it for one like for the Anton Java plateau, which is very dry and reduced, and it's also a submarine eruption. This is we track how sulfur degassing. We can see SulfurX really starts to come up really shallow, and because it's submarine, so it's kind of really suppressed the sulfur degassing there. And then another application is you can model FO2 change, how sulfur and the ferrous iron ratio change along degassing. These are the melting inclusion data again. So this one is a little bit difficult, more complicated. So I got all these steps coming here, right? You want to choose the suitable iron sulfur speciation model, and all these steps, what parameters we just went through, you can actually adjust to make it run better. So the last degassing I'm going to talk a little bit more about is really to interpretation of CO2 sulfur ratio in the volcanic gas. So for many arc volcanoes, we kind of see these two modes of CO2 sulfur ratio in the gas. So one is kind of constant during like quiescent degassing. Right, so here, another time is actually a few weeks before eruption, we might see the surge of CO2 sulfur ratio increase just before eruption. So this is the gas data for Turrialba volcano in Costa Rica. An application I worked on is actually really to use SulfurX to interpret, okay, what does these two modes of CO2 sulfur ratio degassing come from? So these are, again, the Turrialba gas data from 2014 to 18. We can always see this gas surge, right? So because SulfurX can model this CO2 sulfur ratio. So the way we apply to it is really to model what is the CO2 sulfur ratio change in the gas. So these are the SulfurX model results. So then we compare to the observed gas data, then to infer, okay, this quiescent degassing, so this is the gas data, and then compare to the SulfurX modeling data. So we say, okay, so this quiescent gas is more likely to come from the depths between 100 to 200 megapascal, corresponding to 4 to 8 kilometer depths. And then for the pre-eruptive gas, apparently it has higher CO2 sulfur ratio. It comes from pretty deep, but these deeper depths between 12 to 18 kilometers also kind of agree with the melting inclusion entrapment pressure. So this is another potential usage to apply SulfurX to interpret gas data. The last thing I want to talk a little bit about is how do different degassing models compare, because there are many data degassing sulfur modeling sulfur degassing models out there. So in my 2013 paper, 2023 paper, I kind of compared to the older model. So many of them do not do very well to kind of model this melting inclusion data. But then in the Turrialba paper, I compared to one of the newer model. So this black sets is from another model. So we can see we're actually getting pretty close here. However, for the gas composition, if we come back here, so these are this EVO, which is from Liggins 2020. So we can see, even though for the melt composition, the model are pretty close, but then if we compare the gas data, gas model results is actually significantly different. And that is because it's a ratio in the vapor. So it's really sensitive to a very small change of how much sulfur is predicted in the melting inclusion. So we can see there is a slight difference, right? At a given CO2, some is degas more sulfur than others. So SulfurX predict more sulfur degassing compared to the EVO, which is the Liggins et al. 2020. And that results in really big discrepancy here in the vapor phase. So in order to have this application to interpret gas data, we really want to keep this in mind. There are still some discrepancies among different degassing models. So here is kind of what we wrote in the Turrialba paper. So recently developed models kind of behave pretty good for water and CO2, very similar. Another example for water. So these two models actually behave pretty similar for water. However, for the gas, CO2 sulfur ratio in the gas is pretty different. So what happens here is back to, I think, one of the factors back to the pressure range. We keep, I have been mentioning throughout the whole lecture is that there's really very few experimental data that were used to calibrate sulfur degassing at higher pressure, which, it's very different, right? And this high pressure, a slightly different of how much sulfur can be degassed could result in very different gas ratio. So we had a little workshop comparing all this model. And so if you are interested, you can take a look on YouTube channel. And some new features is I recently implemented open degassing, and then I also implemented a sulfur isotope fractionation along degassing, which is used in this paper. And then there's also this sulfide saturation. This is not quite well developed yet, but that's something I'm working on. Well, thanks.
Thank you. So do we have any questions? I actually have one about the importance of having multi-inclusions data. So you said that it's pretty important to get some multi-inclusion to calibrate some of the input parameters, and then also to compare how the model is doing with decrease of pressure. What if we don't have any multi-inclusions data? Do you think we can still get some of these input parameters from geophysical data, or like anything that could try to calibrate, the source of our melt, or it's something that you would not recommend? Like you would still, allow the user to still use SulfurX without multi-inclusion data, or you will say, oh no, you should only use this model with if you have some multi-inclusion data to actually calibrate your input.
Yeah, I mean, depending on what you want to use for, right? So I keep mentioning multi-inclusion data is because I mostly use it to kind of understand, interpret multi-inclusion data. But if you want to kind of, I don't know, like only use that water sulfur to calculate other things as input, I guess you could just, have a sense of your system. For example, if you want to calculate viscosity change, I would assume it will be really sensitive to water concentration, and then you need to at least know, okay, my system is more like a arc system, could potentially start with 3-4 weight% water, or is my system is more like a morb or ocean island, right, from starting with less than 1 weight% or half weight% water. So I guess you do need some sense, but depending on your application, this is really designed. I don't think it's really only designed for multi-inclusion. I guess it really depends on what you want to do with the output.
Yeah. All right. Yeah, thanks.